advisor is Dr. Yan Fu. Today, I'm glad to have this opportunity to share my research with you. And the topic is about automatic identification of tomato pest, disease, and disorder using convolutional neural net scores. And it's about disease, pest, and disorder, which I will refer as DPD. DPD are major threat to tomato production, and if we not prevent it well, it may cause large loss to the tomato yield. So we developed an accessible automatic tool for automatic identifying tomato DPD in the field. We utilize smartphones, which most of the farmers or pathologists already have. They can use their smartphone to upload the image to our service and receive the corresponding result with a treatment method. And our service consists of 5 deep learning models, which I will talk about in the logic of them later. They are the common DPD in Taiwan, and we can see that there are many kinds of them and really complicated. Even and some of them share similar symptoms. Even experienced pathologists cannot distinguish them using naked eye examination. So, to prevent misclassification, we categorize these 17 DPD into 14 categories. At the same time, we ensure that each category can be treated with certain broad-spectrum pesticides for the treatment method. Therefore, we can prevent the misclassification and provide useful category information to the users. So here's the identification process. After the image was uploaded, here the user uploads the image of tomato field. But we can see that tomato field, we cannot see the leaf symptoms on them. It's instinctive, and we cannot tell what's the DPD on the leaf. So we may reject the image and request user to upload another tomato leaf image. After that, if we verify it's a tomato leaf image, we go to the second model, the leaf type classification model, which classifies the input tomato leaf is of the tomato leaflet or the tomato compound leaf. And tomato compound leaf go to our compound leaf diagnosis model for detection. And the leaflet go to our leaflet diagnosis model for diagnosis. And if we find that the leaflet exceeds the symptom of yellow spots, we will further request the user to upload the leaf back of the certain leaf, of that leaf, since this yellow spot category can actually be distinguished using the leaf back symptoms. After all the process, we return the identification result with a corresponding treatment to the users. Let's see how it works. So after image, they can take it or send the image from their album. Here, they send the image of not tomato leaf. This is not tomato leaf. So the service requires the user to take another tomato leaf image. Here, the user sends a leaf image, tomato leaf image, and the system can detect the symptom of it and tell user what treatment method is recommended. And of the third step, when identify yellow spot category, when you found the yellow spot system, it requires user to send the leaf back image. Here, we can do a more precise identification results. So, we use 5 deep learning models to form a multi-stage identification to simulate the logic of to plan doctors' identification logic. And the model will achieve about 90% accuracy and a mean average precision. Thanks to the NSTC for their funding and the Agriculture Institute for their help. Thank you.
Thank you. We have some time for questions. I have a question. How many images you use for training?
About 12,000 images which collect field from Taiwan greenhouse. I can show that. That's the total image you can collect for 5 years.
5 years.
Yeah.
Is this open source data or
Um,
maybe not?
yes.
Other questions?
Didn't you have any data set imbalance problems?
Yeah, it indeed have imbalance data problem, but we use the UOV line architecture, and the imbalance problem doesn't affect the final precision. The UOV line architecture designed to deal with this situation, actually, the loss.
Okay. Thank you again for the presentation.
Hello, I'm reading from National Taiwan University. My advisor is Dr. Yan Fukuo. I'm glad to have this opportunity to present my research. Today, I will be discussing the automatic identification of tomato pests, disease, and disorders using convolutional neural networks. So, the research is about tomato, and we know that tomato is an important crop around the world, ranking as a leader in worldwide production value. However, the tomato production have been increasing steadily over the years. However, despite their importance, disease, pests, and disorder, which I will refer to as DPD, pose a significant threat to tomato production. If not managed properly, DPD can cause substantial damage to fruit yield. For example, research shows that the early blight can cause tomato yield loss for up to 50%, while tomato fruit borer can reduce the tomato yield losses up to 30%. Additionally, disorder in tomato can significantly reduce their marketability. To prevent this issue, identify DPD is an essential first step in integrated pest management. Traditionally, this identification is done manually by experienced farmers or experts. Farmers rely on experiential knowledge to identify DPD. If they encounter unfamiliar DPD, they may seek assistance from government employee expert. However, manual identification can be biased. And while expert identification is precise, it is time-consuming and can overwhelm the experts. Therefore, we need an automatic tool for tomato DPD identification. This tool, you will want it to be automatic, timely, easily to use, and readily accessible. By combining artificial intelligence and smartphone, we can help farmers and experts identify DPD in the field. Farmers can use their smartphone to take images of tomato leaves with DPD and upload them to a service for AI analysis. Here are 17 common DPD in Taiwan, and some of these share similar symptoms, and even plain pathologists can struggle to distinguish them in the early stages using naked eye examination. To prevent misclassification, we aim to leverage AI for identification these DPD. We categorize these DPD by their appearance, grouping those with similar symptoms into the same category. At the same time, we ensure that each category can be treated with a specific pesticide. Therefore, AI can not only prevent misclassification, but also provide useful categorized information for effective treatment. We hope to develop an accessible automated tool for identifying DPD in field. Our solution utilizes smartphone, a tool most people already own. Users can take photos of tomato leaves and receive diagnosis results along with recommend prevention methods. In the identification service, we use 5 deep learning models to form a multi-stage strategy, effectively addressing the complex DPD found in Taiwan. Here's the logic of the service. After receiving an image, the first step is to ensure the image is of a tomato leaf. So we use the anomaly detection model to verify whether it is tomato leaf. If not, like the example of tomato field images, the image is rejected and the user is requested to upload another image of a tomato leaf. Once a tomato leaf image is uploaded, it passes the first anomaly detection step and moves to the second step, the leaf type classification model. This model distinguishes whether the image is of tomato leaflet or tomato compound leaf. So tomato leaflet go to the tomato compound leaf diagnosis model for diagnosis, and leaflet go to the leaflet diagnosis model to detect the symptoms. And when detect the yellow spots, this category symptoms, we further request the user to take the image of the leaf back, which since these two disease, powdery mildew 2 and leaf mold, can be distinguished through the leaf back lesions. So after the identification, the result with the relevant treatment will send back to the users. Images of tomato leaves exhibit symptoms of DPT were collected under various conditions to capture comprehensive symptomatic expression. These images were used to train 5 deep learning models. And when during collection, we ensure that each image were curated by plant pathologists. The conditions of the image varies by season, location, cultivation approaches, and tomato varieties. In total, about 13,000 tomato leaf images were collected. So let's see the first model, anomaly detection model, which filter out irrelevant images that do not show tomato leaves, since this imaging may cause the identification service misclassification and lead to error and result in incorrect information being provided to users. The model pipeline comprises 3 stages: feature extraction, feature projection, and anomaly detection. The extraction stage comprises 2 different models, a teacher model and a student model, which teacher model used to extract spectrum features to identify whether the input image is of a plant leaf, and a student model focuses on features specific to tomato leaves to identify the plant leaf is indeed of a tomato leaf. After feature extraction, the features are projected to a predefined feature space to calculate their similarity to tomato leaf features. This results in a distance measure representing the similarity to tomato leaf characteristics. And finally, this distance is used for anomaly detection, utilizing a simple support vector machine classifier to distinguish anomaly images. For training, 1,000 tomato leaf and another non-tomato leaf image were used to train the ADM, anomaly detection model. And finally, the model reached a 93% accuracy. Next, the tomato leaf image is sent to the second classification model, the leaf type classification model, which determines whether the input image is of a compound leaf or tomato leaflet. This guides the selection for the appropriate model for diagnosis. For those unfamiliar with compound leaf, they are large leaf consisting of multiple leaflets. So we use the convolutional vision transformer, which I'll call CVT, for the leaf type classification model. To train this model, we collect about 2,000 images to train the model. Overall, the leaf type classification model achieves an accuracy of 95%. After identifying compound leaf images, they are processed by the compound leaf diagnosis model. So this model can determine the compound leaf is infected by a virus or damaged by fetal hormones, or it's just a healthy compound leaf. So we apply CVT to train this model, and about 1,000 images were used to train, which finally reached 99% accuracy in testing sets. And for leaflet, we use leaflet diagnosis model for identification, which is the main identification process in the service. This model can identify a certain category of DPT and works on the upper surface of the leaflet to detect and categorize the lesions. we apply ULB9 architecture for lesion object detection and train it using about 18,000 instances. I use a compact version of ULB9 and train it for 100 epochs. The confidence score threshold was set to 0.5 and NMS IOU threshold set to 0.8, and which finally achieve a mean average precision of about 88%. So let's see the different instance of the model. The model can correctly identify, localize, and categorize lesion on a leaflet. Even the tomato leaflet is under a complex background and or has multiple symptoms on the same leaf, the model still can successfully localize and categorize all of them. The final model is our leaf mode and powdered mildew 2 model. To distinguish between the leaf mode and powdered mildew 2. These two models can be further distinguished using the leaf back, and we use the CBT architecture to identify these two TPD, and using about 800 images for training and testing. Finally, the model achieved accuracy approximately 99%. So in the service, we have multiple deep learning models, and we have to use a controller to communicate between the 5 deep learning models and the front-end chatbot. We employ Python and Flex to coordinate the operation for the service. Next, let's discuss our chatbot, which provides a seamless way for user to upload images of tomato leaves and receive a diagnosis, along with recommended treatment options. We have chosen Line as our chatbot interface application, since it is one of the most widely instant messenger application used in Taiwan. So this is the design of the user interface for the chatbot. User can add the chatbot as a friend to identify tomato DPD in the field. Now let's see how it works. Here, a video recording of an example usage of the process. So user can upload an image from their album or tag a new image of a tomato leaf. Once the tomato leaf is uploaded, the identification result is returned to the user, and it only takes just a few seconds. We also provide relevant management method hyperlinks. So these links direct user to the web page developed by the Taiwan Agricultural Research Institute, offering corresponding treatment information. To sum up, this study proposed a system for automatically identify DPD symptoms on tomato leaves in the field, and the service provides a chatbot offering users seamless access to the service. It includes 5 deep learning models, all achieving precision and accuracy of around or over 90%. The service is integrated with the chatbot and is fully automatic and is available 24 hours a day, and is one-stop and readily accessible. It has and is simulating the logic of the pathologist in diagnosis tomato DPD. It has the potential to enhance the efficiency of managing tomato DPD and reduce the workload for experts. And we'd like to extend our thanks to the National Science and Technology Council for their financial support. And we want to show the thanks to Agricultural Research Institute for their assistance in domain knowledge, disease recognition, image collection, and their valuable expertise. It's through our collaboration with them that we have been able to develop a practical identification system that benefits precision agriculture. Thank you for your attention.